Hi, everyone. Good morning. Yeah, it's a pretty early morning, right? Yeah, as Wanlun said, I just arrived 3 hours ago to Taiwan. So I think right now I'm pretty awake, but in a few hours I'll start, falling asleep a little bit. So please keep me awake. Today I'm going to talk mainly about reinforced learning and some of my research topics around it. So first 2 lectures, I plan to give, little details, information about reinforced learning, some technical details too. And my last lecture, on the third lecture, it will be mostly about research topics, some of my papers, and some of the other ongoing research. So I think first 2 lectures will be a little mathy, but the last lecture will be mostly visual, essentially. Okay, so let's first talk about who are you guys, actually. I really don't know too well about you. I want to get at least some understanding about your background. So I see many of you guys are very young. So I'm assuming many of you are maybe also from undergrad students. Is that right? So how many of you are undergrad students? Or none of you? OK, 40 people. But I only see 2 hands. OK. I see. OK. And then others are grad students and some other people from industry. There's no one from high school here. Is that right? OK. All right. Just double checking. OK. And OK, I have one more question. How many of you actually ran and have some good experience in deep learning here? Anyone? Yeah, just whatever you think. OK, who has no experience in deep learning? Then let's put it that way. No. OK. Some of you. How about no experience in reinforced learning? A lot of people. So everyone has experience in reinforced learning here? Oh, OK. So then my first lecture is going to be wasted now. OK, that's good. So let's first start with a very basic stuff. OK, so I'm sure you guys know about Siri and all this AlphaGo and poker games and also self-driving car. And now also people play Dota games now with AI, right? And you also probably heard deep learning is very trendy. I mean, this is very obvious in this lecture, I'm assuming, right? You can see in 2012, there were only a few papers in our archive that talked about deep learning. And now in 2017, it hits about 2,000 papers, right, on archive if you search. And it's increasing more and more. So about 5 years, the amount of papers increased by 3 magnitude. So it's crazy. And as you all know, also deep learning is impacting everywhere now, right? I mean, it's different. Obviously, it's touching on machine learning, computer vision, and language, and robotics, and also medical applications, and finance, and many more things, right? And as you probably also have seen in the, on the web or on your own experience, we use deep learning to create art pieces and or find objects, an object in the videos. Oops, is it playing? Nope. OK. You probably have seen this as well. And also we use deep learning to find objects at a pixel level, which we call a semantic segmentation computer vision, or find 3D objects, 3D pose of the objects in the image as well. And human pose, right? You see there are a lot of human pose sticks. We can just, in real time, we can detect all this human pose from the videos now, too. And also, we have image. We can generate caption from it, too, using deep learning as well. Or we can even do now from caption to image, right? And even further, we can ask a question about image as well, right? So actually, they have an online website you can go and search, right? If you have an image and you ask a question about it, and it will answer it for you, right? And not only just in vision, we also have machine translation, right? We can type whatever text. So it's actually the text I typed on Google Translate. So it's a CS590 is the class I taught before. And then I translate it, and you can see it's translating. I don't know if the Chinese version is correct. I can see at least Korean version is correct because I can read Korean. But I think they're pretty accurate in general. And you can even translate very complex text as well, too. And then, so now with Google Translate, at least you get the idea of any text you can find online. And just a general question answering without image as well. You can have it done. And you can also take out video of a human face and pretty much make follow the facial expression, and also finding cancer as well, right? So at this point, probably, if I know you guys are all like have experiences, deep learning is motivated. You probably all are familiar with deep learning is weakly motivated by human brain as well, right? And over 3 slides, I can go over history of deep learning. One first idea came up in 1982, which is called neocognition, and it introduced the very first basic model of deep learning, and then there was AlexNet. This is LeCun-net, right? So Yann LeCun proposed one of the simple deep learning architecture for digit recognition, right? And then later, recently, AlexNet came up in 2012, and that's basically the start of a hype or boom of the deep learning as well. But this looks complex and whatever. But deep learning really is just it's a matter of one function, right? So we have one input image or one input data point, and we learn a function that can map to the desired output, right? That's basically what we do, right? And we can see this, right? In object detection or object detection in video, right? We are given an image as an input, and we generate output, right? We create a label or a bounding box. And we have a semantic segmentation, same thing, right? We have image, we have desired output, which is a pixel level labels, right? And same thing for pose and so on. This might be too basic for many of you right now, right? And we can go on and on, but I will skip this detail for now, right? So we have description, text description as input, and we can generate output as well. And then we have question and answering and so on. So for CNN, right? Basically, for example, if it's object classification, right? We have image, we convert it to image form, image vector, and then we run through this AlexNet, for example, and then we can get output, desired output, like a car. And if it's RNN, as example, right? It's a text generation from image. Then we have an image of a human, which is my student in this case. He's actually a Taiwanese student in my lab, PhD student. And then we can extract the features, and we can generate a text one by one. Actually, it's what he actually said, so it's not like I made it up. So he claims I said I will put in the class lecture. And then you probably heard of GANs as well. I think that there is a generative model lecture tomorrow. Or did it already happen, or tomorrow? OK, yeah, so you will hear more about this. And there's more and more of this, autoencoder and variation autoencoder. Yeah. So far I showed some examples of detection and semantic segmentation, and question answering, image generation, et cetera, right? But mostly all these topics I just talked about is a lot about supervised learning or unsupervised learning, right? So which means, in supervised learning means we have one input, and we have desired output pairs for every single data point. And unsupervised learning is completely the opposite of it. We have a lot of data points, input data points, but we actually don't have desired output pairs, okay? Right, so this is about supervised learning and unsupervised learning, and these are the most techniques to use for all these problems I've listed here. But there are more than this, right? It's not just about fully supervised or unsupervised, and there are more problems than just this is some of the problems I listed here, right? So for example, humans or even robots, they need to learn to walk, right? And you might have seen this video, right? We want to be able to train a machine that can learn to walk or learn to act, right? And not only just the walking, we also want to be able to train robots that can pick objects as well, right? So I don't know how many of you have seen this video, but this is a work done by Google. So they actually, in order to train machines, they bought like 20 different arms, and then they train the model and keep trying to pick up the object until it succeeds. Okay? And not only just picking the objects, we also care about navigating, right? We want to be able to train a robot that can navigate the room or the space, right? And the more advanced version of this is what you heard about in autonomous driving, right? So we've trained agent as well that can actually drive around by itself, okay? But even all this seemingly complex problem actually boil down to learning in one function, right? If you think about this learning to walk, okay? It's again, same thing. There's input, which is current state. And current state in this example means like a current pose. So when I'm at this pose, what is my next action? Like how fast should I move my arm or leg or neck and so on, right? So what's next action, okay? Right? Same thing for navigating, right? If you think about it, where the input will be where I want to get to, and also what is the current observation, right? So what I'm seeing right now, and based on this, I decided, okay, should I move forward, or should I turn left, or should I turn right, right? It's the same one function trick here. Okay. So the really important question of deep learning in general is how do we learn, or how can we learn this function, right? And that's where everything comes down to. So now for the rest of this lecture will be about how do we learn this, especially using reinforced learning techniques, okay? And what is reinforced learning here? So let's first think about how humans, like us, learn to act, especially when we are very small. Let's take a look at this video. This is my son. If you see, he just try random things until he succeeds, and he sees how his mom is doing it, and he's very happy to see this, so he tries again until he succeeds. And that's what he keeps trying until he succeeds, or until he feels like he succeeded something, right? And if you think about this, if we abstract this into the agent world, this is what the reinforced learning is basically about. So there's an environment where we are physically surrounded by, right? And there's an agent, like us or robots and so on, okay? And what happens is we basically observe, so agents observe what's the environment, where you are, what kind of state you are. Is object standing, or is it far away? Or am I in the room? Am I outside the room? All this information is coming through observation of the environment from the agent perspective. And that's what we call as a state. So we have a state observation, okay? And so once we have agent that can observe the environment as a state, then agent can take an action. So I push my arm, or I punch my arm, right? And I can do all these different things. And that's basically action. Or turn left, or I eat food. So this action can be as abstract as you want it to be, or as discrete as you want it to be too, right? And so you take an action. And once you take an action, you get the reward. So you get the reward in the sense of, did I take a right action, or did I take a wrong action? And this reward can sometimes come immediately, or sometimes it comes very sparsely. Meaning, if I move my arm left right now, I don't get any reward really, right? But suppose I somehow grab this coffee, then I probably will get some reward, because I'm pretty happy to get coffee right now, right? So that's basically what you call as a reward. And then as you take action, you get to next state, right? If I walk right now, I got to new state. If I walk again, I got to new state again, right? As I keep walking, I get to different state and again and again. And I get different observation as well over time. So I keep repeating, or agent keep repeating it, right? And agent can be basically robots or humans, or you can also think about games. In the game, there are a lot of small agent, right? That's basically characters in the games. Or in AlphaGo, the agent can be just a player in the Go. And then so you get the new state and reward, and you take another action again, and then you keep repeating it again. You get the new state, take action, you get the new state, and take action, and so on. Keep repeats, right? You can create a loop of the world in this form. Okay? So one key difference of this setup from especially from supervised learning, is all this feedback, in other words, reward, or whether you did the right thing or wrong thing, is coming indirectly, just in the form of reward, which can be even sparse or sometimes be very dense, but it doesn't matter. And reward is not, it's a very different from supervised learning, it's supervision. Because in the supervision, I will tell you what action to take exactly, right? So I can tell you, okay, you should move left, you should move right, or you should jump, right? I can tell you immediately one by one. So I can give you supervision about your action directly, versus I can just tell you, okay, your current action, if you turn left, I say, okay, that's a score 3, right? And if you jump, I say, okay, that's a score 7. And I can keep giving you some sort of a feedback this way. Whereas a direct feedback would be more like, okay, you should turn left right now, or you should turn right. If not, you are wrong. And that's that's a different form of feedback. Okay. Is it clear so far? Okay. Oh, by the way, if you have any question, please feel free to ask me anytime. Okay. I prefer to be interactive as well, not just my lecture is. Okay. All right. Anyway. Right, so this is this setup is basically indirect feedback setup is where this reinforced learning algorithm comes into play. So there's an agent which is surrounded by the environment. It takes action, you get the reward, and based on this, it keeps learning what is the best way to move around, what is the best action to take at a time. Okay. So for example, this is a very classic problem of reinforced learning in robotics as well, and which is called carpal problem. So all you can do, there's this black box. The only action they can take is either to move to left or to move to right, okay? And then to balance this pole. So by keep moving around, you can see, this way, obviously it's not balancing it right now. And our goal is more like keep moving around so that you can keep having the pole balanced upward. You can see it's moving around a little bit, right? So we do this with the hand as well sometimes. Like I try to do balancing like this just by moving around a little bit, right? So this is a carpal problem. And not only this, obviously there is more classic popular ones now, which is called DQN algorithm on Atari game. You probably have seen this video or at least played this kind of game before, I'm assuming. Is it playing actually right now? Oh, I think it's just a slow. So you can see in this case, the goal is to move this bar around, to move to left or right, so that you can clear these blocks up, right, up at the top, right. And the agent in the beginning was very bad. It just kept moving to right, doing nothing, no meaningful actions. But as now it trains, you can see it's starting to move, make a reasonable behaviors. And at about 34 hours of training, it looks like it's almost finishing the game as good as humans can do. And this is also trained by one of the popular reinforced learning algorithms. And as you train longer and longer, it can be more efficient, it can be faster, and it also doesn't die as quickly anymore. So it's also, again, reinforced learning setup, right? Because there's an environment, which is this blocks, and there's action you can take, moving to left or right, but you don't actually get supervision directly, whether to move to left or right. All you get the reward is that how many blocks you cleared, or whether you died or not. So that's a reward, right? Whether you died or not, that's a signal whether you're doing well or not. And how many blocks you cleared, obviously that's also a signal how well you are playing the game. So based on this reward, basically based on this observation, you can keep training this agent to play the game. Okay? And again, same thing for robot grasping, right? We showed earlier. So what is a reward in this case? Yeah, exactly. So whether you were successfully picked up object or not. So that's a reward. And what is action? Yeah, how to move your arm. Basically torque in your arm, right? Whatever force you have to put into this joint or to your finger and so on. And that's basic action, right? And the state is current pose of the arm and where the objects are, which it can be either coming in the visual form or any other form. Yeah. It's pretty interesting to see this. Sometimes I feel it's pathetic a little bit too. And you have either heard again and seen this video, Mario, right? It's the same. You have environment, which is a Mario game environment, right? And the agent, which is a Mario, decide to whether to move to left or right, jump or run, and so on. And that's action. And the reward is how long you survived or how many you kill and so on, right? Is it clear? Okay. And probably second to last examples, locomotion, learning to walk again. It's the same. There's environment, right? Physical environment. The agent, which is this leg, it learns to walk. And what the reward in this case would be how long you could walk without falling. Okay? So how long you didn't fall. And the action is, again, torque on your legs as well. Okay? And you can apply to navigation, as I said. It's same. You turn left or rotate, you move around until you find the object you care about. Okay? And you get the reward when you find the object you cared. Okay? So I showed some applications in reinforced learning, right? Cartpole, Go, poker, Atari, and actual robotics examples too. So why do we care about reinforced learning? I mean, there is a supervised learning and supervised learning. I kind of told you the answer already, but what would be the reason we care about reinforced learning? Anyone? So the one answer was we only need the reward. Yeah, that's also true. Any other suggestion, thoughts? What is it again? Yeah, we don't need a lot of training data. Sure, it's a partially correct, yes. Depending how you interpret it, yes. What is it again? Yeah, so we need the agent to interact with the real world, yes. Okay, no more? Yeah, I mean, I think my answer was actually just a mix of all these three answers too. The world is full of interactive feedback, right? In other words, we can train a reinforced learning agent only with reward, right? And in an interactive form. Okay. The reason I said partially correct for the training data only is because in the reinforcement you still need a lot of training data, but without supervision though. The training data doesn't have to be supervised, but the number of iterations usually is pretty large, meaning it gets a lot of training data. So depending on how you interpret it, it's partially correct or incorrect. That's what I meant. But yeah. Okay. So again, we talked about, I showed this graph, right? The agent takes an action to the environment, and you get the reward. Sometimes immediately, sometimes it's later, and then you also get the observation or current state back from the environment. Okay. So now let's take a look at this a little more in details. So I don't know how many of you heard of Markov decision process, MDP. Is everyone familiar with MDP here? Or no one heard of it before? I cannot tell. I see. How many of you are actually undergrad again? I only see one hand. I heard 40 students here are undergrad. Okay, I see. So you don't raise a hand here. Okay. Maybe they are just about to enter the graduate. Oh, I see. Okay. So many of you graduated from undergrad. Ah, I see. Okay. So it's a little complex. Yeah, it's okay. Undefined then. Okay. All right. Anyway, Markov decision process. Let me tell you a little more about Markov decision process as I go then. So there's environment and agent again, right? And you get the state from environment, and the same stuff. You take an action at a time t at current time, right? And then you get the reward, or sometimes you get the reward later, and you keep repeating this, right? And that's basically again this assumption of MDP, where Markov property here is very simple. So only thing that matters to decide what action to take is the current state or current information you have. What does that mean? So there's more, it can be more well-defined in mathematics, but roughly saying, this means that you actually don't need to know the past history to make a decision about your next future. So you only need the current information, current state information, to make a decision about the future. Which is obviously a very, very hard assumption, if you think about it, right? This is usually not true in the real world, but this is an assumption you can make, or you make a lot of problems in reinforced learning, so that you can simplify the problem formulation. Because otherwise, you have to look at all the way to thousands of years ago, which is just way too much information to train the data, or something you don't even have those data to begin with. Okay. But it also holds true for many situations too, right? For example, if you're playing Atari game, you actually don't need the past information. You just have to have current information to play the game. Many real-world examples also doesn't have Markov property, but with having this assumption doesn't hurt as much. Okay, while it's not even exactly true. Yes, go ahead.
But you have a fundamental trade-off between memory and then having to include history. So what you always can do is that you can introduce states that act as memory containing the information of the history. So therefore, you can always fulfill this property.
Right. I mean, one is there are multiple reasons. So, yeah. So one is actually sometimes you just don't even have access to those past history, for example. Right. I mean, if you're talking about, let's talk about human history, right? We don't even have access to 5,000 years ago data at this point. And I don't even have data point of myself when I was first year old, right, for example. So sometimes you just don't have access. And the two is you don't have enough data memory to stack them, or even for the training purpose, you don't want to have 10 years of data as input. Then basically the complexity of training gets too complex. So sometimes it's more of a trade-off, as you said, yeah. Okay. But is it clear what the Markov decision, Markov property here? Okay. I think this is as simple as it gets. You throw away all the past information. You only see what's there right now, and you make a decision about it based on it. Okay. And the way we define this Markov decision process is you have a state, right? Basically a current state, what you see, right? And then what action to take, and then distribution of reward, which is R here, and then the transition property. Sometimes, basically, because it's a little technical, but when you take an action with intention to move to left, sometimes you don't actually get to move to left. Maybe because there's a wall, so it will block me, right? So I told my agent to move to left, but even if I'm tempted, if there's some wall here, I try to move left, but I will get bounced back, right? So I cannot move to left and so on. So there's this transition probability, which you can kind of ignore for now, but there's some complex situation sometimes your action doesn't get to the reward, the desired state you care to. And there's discount factor too, which is related to reward. Again, you can pretty much ignore, but discount factor just means the longer you have to wait, you care less about that reward. Okay? You care much more about your current reward rather than your future reward. That's far ahead. I mean, it's the same for human, right? Even if I tell you will win $1 billion in 1,000 years, you don't care at that point, right? In 1,000 years, $1 billion for you is meaningless, right? But if I tell you, you probably prefer to have $100 in 1 second over $1 billion in 1,000 years. For many of you, I think. At least I would prefer that way, right? So that's kind of discount factor. The longer you have to wait for big reward or even small reward, you care less about it, and you prefer the immediate reward or nearby reward. And so that's basically a discount factor. How much you want to discount it is a discount factor here. Okay. And as I mentioned, many Atari games, as well as this Pong game, basically bouncing ball back and forth, has a holding this Markov decision process, MDP property. And many games, even if they don't hold it, in reinforced learning, we usually make this assumption. We just assume that current state or a few states before this current state is enough information to make a future decision. Okay. So in Atari games, our objective is winning the game, right? The state, which means usually just raw image pixels, right? So where the ball is, where the current object is, and all that, right? And the action is you move to left or right, or this kind of what kind of buttons you push, right? That's a basic action. And the reward is positive and negative depending on the score. You win or you lose, right? You eat some good items, that's a reward, okay? And Dota games, same thing. Objective is winning the game, and your state is again raw image pixels, and action is game control, right? Moving to left or right, hit, and that's etc. And reward is if you win the gold, you earn some reward. If you actually completely win the game, you get bigger reward and so on, right? So that's basically how you. And this reward. This reward, by the way, is not predefined. So you can define your own reward. And that's very important, by the way. In reinforced learning, designing your own reward is very important. So for example, I can just give you a reward in Dota game. Well, maybe you're not all familiar with Dota game. Let's take a look at maybe just Atari game, which is a little simpler game. So I can just give you a reward only when you win the game. But that again, it means you get only one reward only at the end of the day. But suppose you just imagine yourself, you didn't know anything about this game at all, but you get the reward only when you finish the game. That's just very, very sparse. So you probably will never get, even for humans, in that case, you will never understand what the game is all about, right? So sometimes it's preferable to give a little sparse reward or a little more dense reward here and there. Oh, you're doing well. Okay, so that you hit the block. Okay, that's a good reward. And so on. So you give this a little more sparse or a little more dense reward than just giving one reward at the very last game or at the very end of the game is more desirable. But the more and more dense reward you have to design, one, it becomes pretty tedious. Sometimes wrong design of the reward can hurt the training too. And this is a human decision. So where the human has to come into play and you have to decide what reward you will give. And that's what we call a reward engineering. Okay? So for example, the same thing in Dota. Typical Dota games, I think, last 20 to 40 minutes. Correct me if I'm wrong. I don't play Dota, but I think it takes about 20, 40 minutes. And imagine yourself, you keep moving around randomly, and you get one reward only at the end of the game, which is after 40 minutes. You'll probably give up even before the game finishes, right? Whereas if if you get some reward if you hit the enemy or if you get gold and so on, you will start to get the idea of the game a little quicker, right? If you have no assumption, you don't even know anything about it at all, then it's really hard to train even yourself to play a game just by one reward after 40 minutes every time. Okay, and there's a go. And again, it's also again about winning the game, right? And the state is a position of all the stones, and the action is where to put the next stone. And the reward in this case is 1 if you eventually win the game, or 0 if you lose, right? Or you can have different reward as well. If you do correct move or better move, we can give reward and so on. But I think in AlphaGo's case, they actually gave reward only when they win or lose. One reason is because it can be very quickly trained. Because you can imagine, Go is a very simple environment. You can keep playing it. It's a lot of move, 200, 300 move, but in the computational time, making move in a Go is very quick. So, it still is impressive that they could learn with only one reward function. And they had to play a lot of different tricks to do it. But at the end of the day, that's the one reason. Whereas a Dota, you cannot really simulate it over 1 second. Whereas over 1 second Go you can probably finish thousands of games over 1 second too. Okay. All right, and also again robotics. Robot learns to move, like for example walking or navigating or etc. And then state and action. It's pretty obvious as it is now, and you get the reward when you make time steps or you survive, and different kind of reward you can design as well here. Okay, so again, this is what we call as a Markov decision process. We showed what kind of cases they are. So, what does this MDP or this functions or this defined definition of the MDP world means in the real world. So let's take a look. So at a time step t equals 0, we have initial state, right? This is how MDP works here. And as time goes on, you keep looping, so time increase, t will keep increasing, right? So at time t0, agent takes an action, right? So a sub t, right? So you take some action, and you get the reward. So environment will sample the reward for you. So you get the reward RT, which is the reward at time 0. And then also environment will also sample the next state based on current action. So based on current action AT, the environment gives you back ST plus 1, in which case S1, right? Based on some transition function probability I just said earlier. And agent will receive this reward then, and then also this next state, and then again it will keep looping. So now then, if based on this new state and reward, the agent will take a next action, AT, right? And then again, it gets the reward from environment RT and ST plus 1, and you can imagine it keep looping over and over and over until it ends. Okay? And here's a new term here. So here's a new term I introduced, which is policy pi. Okay? And policy is a function of from S to action for every possible states and action pair you care about. Okay? So policy will give you what kind of action to take for given state. Right? But what would be the goal? We want to find the optimal policy. Right? Policy can be anything. So I can just, if I keep moving to right without any purpose, that's also one policy. It doesn't have to be good policy. Right? I just keep moving right now without any intention. It still is policy. Right? But now if I drink coffee or if I speak, that's a better policy, probably at this point, right? And it's a little better policy. And if I give a best lecture, that's an optimal policy, which I don't know how to do exactly right now. But that's called finding optimal policy, pi star. Okay? And in mathematics form, finding best policy means optimal policy will, by definition, should give you the best reward in current MDP setup. You can note here, right? So you accumulate t over time with some discount factor, as I said. So you apply some discount factor. So the farther away, you get less reward about. You care less about the reward. And when you sum it up, this is the total reward you get about this current policy, and you care to get the maximum total reward. And that's basically the optimal policy. Does it make sense? All right, is it clear until now? Any question? All right. No question? Yes?
For that, all of the best policy that you just showed there, that's the reward, that's the accumulated reward.
Yes, it's a what was it again?
That accumulated discounted reward, that's into the future, or?
This is looking, so given current policy, this is basically the definition of total reward of any given policy. And when I say you want to maximize, so you by finding a policy that maximizes this total reward, we could define it as an optimal policy, right?
Right, but what I'm asking is you're summing over all time t, right?
Right. From time 0 to until it ends.
So that factor, this discount factor?
Right, discount factor is here, and
That
gamma. Yeah, discount factor is usually less than 1 or equal to 1 sometimes if you care. But usually it's less than 1. And the smaller it is means you care less and less. You care only about immediate reward. The closer to 1 you mean even the future reward is as important to you. Right? Yeah, you call it as accumulated total reward. Any other question? All right. Okay. Yeah, so again, finding optimal policy means this basically finding a policy that gives you the best cumulative reward, which is defined in this summation form here. Okay. And let's take a look at this in a more simple MDP world, where I show you here. So so imagine you can have 4 different types of action you can take: right, left, up, down, right? And there's a state, which is basically this kind of, you can imagine this is like a simple maze, right? You can move around, right? And and your objective is to reach these stars with the least number of actions, right? So now let's think about how to formulate this in the NDP, okay? So we set this getting to the star as reward equals 10, which is arbitrary. I picked the 10 just because I feel like it, right? We can define different kind of reward. You can even give a negative reward, but obviously it's undesirable. You can give 100 or 1. It will all have different impact. Because if you give a small reward, depending on the discount factor, you may start to don't care about it as much. Suppose your discount factor is 0, which means you care nothing about your future reward, then getting to this star will just practically means nothing, right? If you have a small impact discount factor, also same thing and so on. So that's one of the reasons the reward designing is very critical. But that's a very manual and tedious sometimes. So sometimes you need a good intuition about your environment to design it. So it's not like the reinforcement learning is a black box. You can just port it and then hope it works. So you have to understand the environment pretty well so the humans design the reward accurately and so on. And then also, you give a negative reward if you take an action. The reason we give negative, does anyone know why we are giving negative reward here for taking an action? Anyone? Yeah? Yeah, so the answer was to get to the shortest path. What does it mean? As you take action, you get a negative reward, which means you try not to take any action, right? Meaning you will try to minimize number of actions, right? Because the more action you take, you will get more, you will harm yourself, right? So the agent will try to minimize it action. But then now let's make it a little tricky here. I just realized it's fun to talk about it a little bit. So now we have only moving right, left, up, down. And let me show you why reward design is important here. Let's suppose that we have 5th action, which is doing nothing. Okay? Suppose the 5th option was just staying as where you are. So now we have this negative reward for taking an action. What will happen? It will not do anything. Because it just preferred not to do anything so that you don't get any negative reward. Because suppose your future reward is not big enough. But if the positive reward here was like 1 million, then probably the agent will start also again move around because then you get this reward which is very large, even with some penalty of moving here. Okay. Right. Okay. So this is one setup, a simple setup of a MDP world where here on the left, it's one of the policy, which is a random policy, as I said. And the random policy is a policy still, right? It's a bad policy, but it's not. It's still a policy. Where on the right side, I show the optimal policy, what action to take at every current state. Sometimes you can take 3 actions here, because any of these 3 will be will lead to the optimal result, right? And sometimes in some state, you only have one option to make a best action. Okay, and on the left side, a random policy means you just take whatever random action at a given state, and there will be different policy which could be suboptimal too, or sometimes you can make it the worst policy too, which just keep moving around but without getting to the reward too, right? Yes.
In order for this optimal policy to be optimal, you need to define the discount factor and also
right.
the
exactly.
exact value of the rewards.
Yeah, exactly. Exactly. Yes, exactly. Which is coming from here. All this, when I said this optimal policy here, it's based on this current assumption of the reward and discount factor. Okay. So depending on the reward and discount factor, this optimal policy will not hold anymore true, right? Because if you think about it, the reward designing is essentially setting up the game purpose, objective of the game. Right? So let's suppose this was a game, right? We all have some intuition about what the game should be about in general, but I can make a completely opposite game, right? Maybe in the Mario game, the entire goal was to just keep suiciding, right? So then all the reward design has to be completely opposite. Or, yeah, maybe it doesn't have to be completely opposite, but it has to be different. So you will learn different optimal policy for that game or that reward specifically. So I want to keep. I know I'm keep emphasizing this reward designing here because that's one of the key things people keep missing when they're training reinforcement learning agent. Okay. Sometimes it's very obvious, right? Obviously suiciding versus playing well in Mario in our current standard setup is very obvious. But even walking, sometimes it's very subtle to tell whether you designed your reward correctly or not, right? Like playing well or suiciding in Mario is very obvious. So you can pretty much watch a couple policy and start to realize, okay, you have designed the correct reward. But oftentimes, it's very hard to tell whether your reward design is correct or not. And in many research projects, a lot about it is actually coming down to how you design reward, oftentimes. And the ultimate goal of many reinforcement learning, I wouldn't say an ultimate goal, but one of the challenges and one of the very popular problem in reinforcement learning in the current research trend is how to train an agent with as little reward designing as possible, which means you give a reward only when it's very obvious. Like, for example, only when you win or only when you lose. Which we call, in the technical, we call it a sparse reward, right? And the most sparse reward form is that you only give reward when you succeed or when you fail. No intermediate reward at all. But that's a very hard to set up in general, and that's, at the current state of art, we don't know how to train an agent with sparse reward. Okay, and many research is ongoing on that topic too. Okay, so again, as I said, so ultimately, again, in this kind of NTP setup, our goal is to find this optimal policy, and that's what the reinforcement learning is about, okay? And then our goal is to, again, find optimal policy pi star here, which minimize the expected value of total reward, maximize the expected total reward, okay? So our goal is, again, maximize the expected total reward, and we define it more formally, we define it here. Expected value, right? Yeah, expected value of the total reward, so reward and discount factor, right? You can just assume this is a mathematical form of how you sum up all the reward you get based on your action, okay? And then whatever policy that maximizes this expected term is we call as a pi star optimal policy, okay? And with this assumption of all this definition of how likely where you start initial state and what action, whenever you have a given state, the policy will take some action. And st plus 1 this basically is a transition function, which means at a current state and you take some action, what's likely you will get to this state st plus 1. Okay? So this, again, is a definition of the world. So all this at the bottom, you can just think of it as under this definition of the world, or under this world, okay, with all the reward and state and all the action space. How do we find the optimal policy pi? Okay. So let's talk about how we can train at least one algorithm to find this optimal policy, right? So here, let's first talk about value function and Q-value function, okay? So let's suppose we are given a trajectories from S0, state 0, right? And you have action 0, and you get the reward 0, and you now go to S1, and again you take action 1, and you get reward 1 and so on. You keep going on and on. So how do we evaluate this state? So how do you evaluate this state S0 when you are given this trajectory? Or any state? Any idea? So what do I mean by this evaluating a state? So in other words, how do you know how good this state is? So suppose I'm at this current state. For the purpose of standing, right? How good am I? Am I in a good state or bad state? Probably on the edge is probably bad state, right? If I'm here, it's probably safer. So probably it's a little bit higher value compared to if I'm on the edge. If suppose my goal is to never fall down, right? Then probably I'm on the bad state relatively. And then here it's much safer, so probably a higher value state and so on. So how do you evaluate this value of the state? But in a more formal form, obviously. Yes?
You update them by the possible next state.
What is it again?
You update them by the possible next state.
I see. Sure. But I think, I guess I'm more talking about formally a little bit here. Any thoughts? It's very simple, actually. Maybe too simple to think.
To conjecture the goal.
What is it again?
Because you have the objective, so you just to compare your state with the goal.
Right. So in this case, we call it a value function here. With given policy, okay, given current policy of a value, the way we evaluate is basically you evaluate whatever reward you get based on this policy. Does it make sense? So you have a policy, you take some actions, right? Under this so the policy gives you what kind of action you are likely to take, or less likely to take in each state, right? Remember, this is basically policy, right? Sometimes you have random policy, or sometimes you have optimal policy, or you have suboptimal policies, and so on. Based on this kind of policy plan. So in other words, that's a kind of, you can think of policies as a plan, like what kind of plan you have about each state, right? And based on this policy or plan, you evaluate each current state. So in a current state, you can already evaluate all the future reward, total expected reward, based on each action, and you sum it up, right? So if you look at it, basically it's summing up all the state based on S0, or current state with a given policy, right? So in other words, in my current state, what's the expected reward you will get at the end of this policy? And you can evaluate for every different policy. So when I'm standing here, it's one state. I can evaluate all different possible moves I want to take, and then take action, and then sum up all the reward. And when I'm standing here, I can also sum up all this possible move with a future reward, summing up all the future reward, and that's one's value. And that's basically the value of each state. So expected summation of the total reward. So why is it important? Because you can evaluate what is more desirable state to be on compared to others. Okay? So that's about evaluating a state. So now you can also imagine evaluating a state and action pair. So that's a Q value. We call it a Q value. What does it mean? So again, so if I'm standing here, moving forward is probably worse. Leaning forward is a pretty bad action here to take, right? For the purpose of standing. Whereas moving backward is probably much safer action to take. So in a current given state, how good is this value? What is it like? How good is this value? What is the value of moving forward in the current state? Or what is the value of moving backward in this state? And you pair this up, and you evaluate it. That's basically what we call a Q value function here. Okay? Is it clear? Okay, good. So again, there's a more formal definition here, summing up all the possible state action pair values for future reward. Okay. And that's what we call as Q value. All right? Yes?
So how if, so actually how if the, like the reward will be time variant? For example, like in the basketball game, right? Maybe in the beginning when you earn some scores, it doesn't matter too much, but maybe in the end, like when time closes to the end of the game, then you might prefer to defend, to...
I see. Right,
yeah.
right. Yeah. So the question was about this time-dependent reward. Yes, that's basically, it's a one engineering purpose also too. So how, as I said, reward is not really, I mean, usually there's only one ultimate reward we care about is, I mean, for example, for soccer, I think that's the example you gave. The goal is to win, right? And that's very clear reward in general. But even then, it's not clear if whether you should give 100 points or 1,000 points or 1 point when you win or lose. So there's this trade-off still. But anyway, shortening it, time-dependent reward or not time-independent reward, how to design it is your choice or human's choice, essentially. And depending on algorithm, sometimes time-dependent one is better. So if we are Oracle, if we are God, then probably we want to give as dense reward as possible on every single move. At a time t1, we move our left leg, and then on time 2, we should move the right leg. Then it becomes a very supervised learning at the end of the day too. So how sparsely you want to give this reward and how much value you give about each action, or should it be time dependent or not, is all your choice. But the more engineering you give, sometimes can actually make it worse because our intuition is not sometimes as perfect as we think it is. So in many training algorithms, sometimes if you give too much reward engineering, it actually hurts too. But it's just a choice at the end of the day, yeah. Okay. Right, so this was about Q value function. So I defined basically value function for state, right? Basically giving you how good is a state. And then Q value function, how good is a state and action pair, which is called Q value function. And using this, we will try to solve, or we will show how to find this optimal policy based on this two function definition. Okay, so we introduced this what's called the Bellman equation. Okay, this is actually a technical term in math, coming from math, but we are applying it to reinforced learning here. So if you think about Q value function, it can be decomposed into two parts. Okay, one is the immediate reward. And the second is the basic discount value of all the successor actions. Okay, so what does it mean? So suppose we have this current state and action, right? Which is Q, and we can evaluate it. Our goal is to evaluate it, right? Q pi SA, which means we want to find how good this is state and action pair, and you can decompose into reward, and you go to successor state S prime. Which S prime, and how do you evaluate this S prime now? We have this value function we define. I told you earlier, right? So V policy of this S prime. Then what happens? So now this Q function can be just decomposed in two parts. The first term is about this reward. When you're at a state S. And when you take action A, you get the reward, right? So that's the first term here. The reward you get at the state S when you take an action A. Okay? The second term is essentially the summation of all the possible actions at S prime, all the possible successor states and their value. I'm just summing up their value of all the successor states, right? Obviously there are different ways of representing it. So this is one version of a Q function, but this is a little more intuitive if you think about it. So basically the value of the current state and action is the reward you get and the value of all the other successor states. Right? And that's the value of the current state and action pair. Okay? Yeah, and this depend. And then I think it's just a special note that each Q value function depends on given policy. Okay? And again, the optimal Q value function Q prime or Q star, it will give the maximum possible expected return. So meaning Q star is a policy that maximizes this expected value of a Q value function, and which satisfies Bellman equation, which means you can just reformulate it. So, but the key thing to note is the reward here is the immediate reward, and then everything else can be reformulated in this Q star here of the successor states, right? And you can, this in computer science, we call this as a recursive function, right? You can use your own function, Q star, to define what is the best policy, what is the best Q star, using its own function here. And you can see this in repetitive and in other words, recursive. And that's a Bellman equation here. And there's a reason we care about this Bellman equation later on. Okay? Which means there's the property of this repetitive property is the way we are actually finding Q star at the end of the day. Okay? So we text, and then once we have this Q star, we can just take action. So let's first talk about this, and before we talk about how we get this Q star, okay? So let's suppose, forget everything else I talked about so far. Let's just suppose I give you this Q star, which means I give you optimal Q value function, right? And what can we do? Then we can just have an optimal policy based on this. How? Anyone? So again, my question was, if I give you Q star now, how do we find optimal policy based on this? Okay. Maybe, yes? Right? Right. Yes, yeah. So the answer the student gave was wherever state you are, right, you can just refer Q star function. You evaluate all these possible actions and take the best action that gives the highest Q value, right? If you already have, suppose you're at a state S, you can try action, you can try moving to left and moving to right. So you can look it up, right? S left, S right, S up, S down. And whatever, it will keep giving you some of the values, and you take the best action. So let's take a visual here. So you're supposing you're in a current state, and you want to evaluate right? So you have this function, which is basically giving you Q value, right? Suppose if I give you this Q value function, you can just put this as current state and right into this Q value function, and you will get some value, right? 0.87. And let's suppose you move to left, and again, you get some Q value function here, 0.94. So you have these two different values. So now what? Because the bottom one has a higher value, right? Then you will move to left, right? Is it clear? So now it's very obvious. So when you have a Q value function, optimal Q value function, you can find optimal policy very easily based on this Q value function. That's all I want to say. So whatever state you are, you try different actions. You don't try action. You actually evaluate your different possible actions. You look it up. So basically, this Q value function is just kind of dictionary. You look it up, right? You have state, and you take action. You look up what's value, and you take a different action, and then look at the value, and text whatever is the highest value in it. Okay? What if you want to do worst action? What if we want to get a worst policy? Can you still use this Q value function or optimal Q value function? It was actually a little bit tricky question. Actually, the answer is no, because this Q value function is still maximizing inside it. When you actually take it, so this Q value function here, if you think about it, you have max term here, that's trying to maximize it. So you actually, this definition doesn't go well. So you have to compute difference Q star, which is trying to minimize the value here. Okay? But anyway, that doesn't matter. Yeah, that's not as important. Just a tricky question here. Okay? So now what? I mean, I told you how to get best policy once you have a Q star, but the problem is how to get to Q star, right? So I told you this is Bellman equation here. So what can we do? I mean, think about this a computer scientist way. I mean, how many of you are computer science students here, by the way? Many of you? Or who is not computer science students then here? Oh, wow. So what are you guys then? Electrical engineering? OK, then who are not from E or CS then? Math? Oh, OK, I see. OK, then other than math students here. I mean, it's just a joke. So how do we evaluate, if you have this function, which I already gave you some hint, how do you actually get Q star from here? I mean, this equation kind of looks scary in some sense, but it's just, again, a very simple recursive function. How do we do this? OK, forget about computer science even. Just what would be your first answer to trying to get some value of this when you have it? Just be elementary school student here, I think. That's the simple, most easy way. We call it as a value iteration algorithm. Sounds very fancy. But really what happened, OK, is this. So there's intuition and all that, but let's forget about this. So you just initialize a Q0, OK? Which means you just have some idea of, you just randomly initialize this Q value function, OK? Q0, all right? And then what do? You take some state and action, and you get the reward. And based on this, you update it. So you have a Q0, right? And you take state and action, and you get the reward. And then you can update. Based on then this, you can update Q1, right? So Q1 equals whatever reward you got plus a gamma. Again, this is just a defined term. So R and gamma is given, right? Because you take action, you get the reward. So you have reward and you have gamma. And then you have Q0 because you already initialize it. You have initialized Q0, just random initialization, right? Then you have all this term here. You will sum them up, then you get Q1, right? And now you have Q1, and what do we do again? You take a different action, whatever action again, and based on this action, you get another reward, and you update it again. Because you have Q1, and you have gamma, and you have reward. So you can evaluate all this, and you get Q2, and you can keep going on and on. And this works because this is a Bellman equation, and that's a part of it. So that's why, and then you call this algorithm a value iteration function, a program. Okay, and you keep doing this until it converts. As simple as it gets, right? You taking, so basically, in other words, you just take actions, you update Q function, you take another action, you update Q function, and you keep doing it, and until it converts. So until it doesn't change the value, or the change is very small. Okay, and that's all you do, right? If you keep repeating it, you will be done. And that's how you learn this Q star, right? When it converts, that's basically when it found the optimal Q value function. And now you have an optimal Q value function. You can apply to any. You can apply to your game or environment, and you will be able to solve the game, right? Cool. Okay, there's a catch here. I mean, I told you in the beginning all about deep learning right now, and now I didn't use any deep learning techniques so far, right? So so far it was about reinforced learning. I didn't use any deep part of it, so it's not deep reinforced learning yet. So where does the deep part coming in? Any question? Any idea? Yes? OK, yes, the Q value function can be deep learning function, in other words. So far, whatever I told you was non-deep learning way, or it's a classic reinforced learning. But let's first take a look at it. So there's a problem here, OK? What is the problem?
Simple space 2
Yes, yeah, exactly. The sample space is too big. In other words, when we train this Q function, we need to have this Q S comma A for every single state and action pair. What's the issue of it in computer science? In math, it's beautiful and it works well, right? So these students should be happy. For all of us, all others, including myself, the problem is that we are dealing with a computer, which means we have a memory issue, right? We cannot stack all the state and action pair for big games in general, right? When we cannot hold everything, what do? We approximate them, right? And so our goal is to approximate this Q value function instead of getting exact one. So all your value iteration, using value iteration algorithm, we can actually get Q star, up to the optimal, very optimal one until it converges, except that we cannot hold all the state and action pair in many cases. Sometimes action is not even discrete, or state space is too big, and it just gets too big to hold into a memory. And that's why we need to many times approximate them, and that's why we are, yeah. And again, it doesn't have to be deep learning here either. But one of best function approximator we know right now is, or one of the most popular one we use is deep learning function, right? So, yeah, what would be a good function approximator? Yes, a neural network. Okay. And told you earlier, neural network is all about just training a function, converging from a input to output, and that apply here too, right? I told you earlier here again. Okay, lecture 3, I'm talking about some other lecture, but okay. Here, given an image, we can get this output and so on, right? I already told you earlier in the beginning. And in this case, we have a state and action pair. We train a function, f, that can map to a Q value. And this f here is going to be neural network now. In other words, Q approximator. Okay? Let me see, how much time do we have? 15 minutes, okay. Right. So here, when I say Q S comma A given theta, theta here is parameters of neural network. Okay? So whatever defines this neural networks essentially. And how do we train this? It can get into a little technical, but I will just skim over how we do this. It's again using this Bellman equation property here too. So optimal Q value functions again satisfy this Bellman equation property, and we use this to evaluate, as I said earlier, and we can use this again to train neural network too. So why is it tricky to even first to think about it? Why is it tricky to train a network like this? So, okay, let's just step back a little bit. So I know it sounds like many of you already have some training experience with this neural network. I don't know how many of you actually use reinforcement learning before, but in a supervised learning setup, it's pretty simple now, right? So how do we do this? You have a desired output, right? And then if the loss you set up the loss function, right? I'm sure most of you are familiar with the term loss function here, right? So what is the purpose of loss function here? You have a desired output, your current output of neural network. You take a difference. You give a penalty if they are different, or you define how much you want to penalize based on difference between desired output and your current output, or ground truth and the current output. Is it right? And that's how you set up the loss function. But why is it tricky here now?
You don't have ground truth.
Yeah, you don't have ground truth. You don't actually have optimal Q value. If you already have a Q value, then you're done. So you don't actually have to just train this neural network, right? But the problem is you don't have this ground truth Q value. So you cannot actually, it's non-trivial to think about how to set up this loss function. In a typical setup, you have desired output and current output. You take difference and penalize it whatever form. Sometimes L2 or L1 or some more complex function, right? But when you don't have optimal output, you cannot do this, right? Ideally, if you have a Q value, optimal Q value, you have a Q value, and you take a current output, current approximation, and take difference, and you keep repeating until you get to the desired output. But you don't have this desired output, unfortunately. And that's a tricky part of it. Okay? But fortunately, again, based on this Bellman equation property, we can apply some trick here. And that's the beauty of it, actually. Okay? And thus, loss function, based on this Q value, this Bellman equation property, what we know is, it's just like previously, when we have this current value, we know the next iteration space, next better. So when you have a current Q value, okay, based on this property here, you can get a little better Q value function, which may not be optimal, but we know at least when you operate under this operation, you will get better one, right? Remember in value iteration algorithm, you have Q0, you devalue and you get Q1. So you know Q1 is better than Q0. And you evaluate, based on Q1, you can you go through this summation and you get Q2, and Q2 is better than Q1, right? So what does it mean? So this is a current neural network approximation, right? The loss function will be basically putting this yi, which is our supposed to be optimal answer, but it doesn't have to be optimal. What we do is we evaluate yi based on this current Q value approximator, which we know this yi is better than at least Q. Does it make sense? Or it doesn't make sense yet? Okay. So yi is essentially evaluated based on Q. So Q here is a current. So during the training stage, this is during the training stage, okay? During the current training stage, you have current evaluator, the current basically approximator. If we had optimal value in the typical setup of supervised learning, yi would be Q star, the optimal Q value. But we don't have a Q star, as I said. So what do we do instead? We try to get better. Instead of trying to get the optimal one at the current iteration, we try to get a little better Q value. Is that clear? Which is, once you evaluate on this, we know this is better than current Q. So you can call this a Q prime, for example. So Q prime. So this part, we know this. This is again based on this Q, current same Q, but after evaluating once. Once you iterate once, it's better than Q. So our goal is at every training step, the goal of neural network training is that we try to improve. We try to make our current Q approximator be slightly better. It doesn't have, as long as it keeps improving, we know it will eventually converge. That's the ultimate goal. Rather than trying to get to the optimal value immediately, our goal is to try to catch up the next step, and catch up next step, and keep going on and on. Yes.
Our goal is to make it converge more quickly.
So it's not in this case. It's just about making it converge at all. Yes. Yi is what? This one? Yeah, yeah, the current state, right? Current Q. So this is a current Q. Whatever, at the training stage, we have some approximator. Even if it's a bad array, we have some approximator. And yi is evaluated based on current Q as well. But when we evaluate based on this current Q, this is still better than, it's a Q prime, which a Q prime is better than Q, based on this Bellman equation property, which is here. So we know that by trying to make it Q prime, basically next Q, we know it's better than Q. So it improved. And if we go next step, then it will try to improve again based on its own next step and keep repeating it. Again, it's a recursive concept.
What are the conditions in order for that to be true? That
So,
it always improves?
that actually I'm not so sure, actually. I have idea. I think I have some idea, but I'm not 100% sure. I will probably not answer it right now. It's a basic Bellman equation property, I think. But I will probably I will be safe about this. So, yeah. So the question was, what makes this to be holding true always? What is a condition? And I said I don't know yet, or I don't know right now. But it's related to Bellman equation. Okay. All right. Okay, and then there's a forward pass and backward pass, which means forward, you evaluate it, and backward, you just update the theta, just as typical neural network setup. So the only thing, the beautiful part only here is that just you substitute this from the ground truth yi in general, which is usually just always ground truth in supervised learning setup. You change it to value you know is better than current state or current function. And that's that's the only change it makes. But only based on this, it makes the training possible at all. Okay? And you update it. You know, it's just derivation. And again, as I said, once you have this approximator, it's the same thing. Once you have this Q star or Q approximator, you can do the same thing, right? You apply Q value, you get the value, you get another value, and you take this value. It's the same stuff. All right. Any questions so far? Yeah, this is one of all the deep reinforced learning work. The intuition of this changing this loss function is one of the contribution of that work. And I'm almost done for this first part, okay? And let's take a look at how to use this to solve Atari game. And that's basically the paper of DQN from DeepMind. Okay? So one thing I made earlier, I said about is that we care about current state only. And this current state doesn't really have to be current single state. And in this DQN algorithm, in this paper, they stack a few previous states together. And you call this as current state, right? So why not just a single state? Because sometimes we have temporal dependency, right? And in fact, it's not sometimes we have temporal dependency. It's actually pretty rare to find it when we don't have temporal dependency. But again, with the memory issue or sometimes data issue, we cannot stack entire history. And even if we want to keep entire history, sometimes it's tricky to train, even if we have memory. We don't have a memory issue. So rather than stacking everything together, we just take a first few previous states and stack them together, and that's how they do. And once they have it, so they stack this some of the previous states. You have convolutional neural network and all this, simple neural network stuff, and you get this value, which is called Q value approximator. And once you have it, you evaluate it, you get the score, and you take best action that give you best Q value function. A Q value, okay? And then now, as I showed earlier, this is an Atari game DeepMind has trained. It works pretty well on many simple games. And same thing for Pong, it works as well too. Now many of this is superhuman makes superhuman performances with more tricks than just simply this, but the biggest high-level ideas are touched over here. Okay? So that's pretty much it for my first part of the lecture. Do we have any question now? Yes? Oh, can you speak a little? I couldn't. Okay. Oh, I cannot hear you well, sorry.
I say the reward function, and just like you talk about the policy, that need to use things
Sorry, maybe you can speak once again with the mic.
No problem.
Okay, hi. That's morality. Okay. I just want to ask, because it's based on the cuteness, I want to ask just like you said, the reward and the policies, that should be defined by the memory or not.
So the question. So let me reiterate it. So your question was, does reward have to be designed by human? Is that right?
Yes.
Yes. I mean, so reward basically defines the game essentially. In other words, you can think of it. Okay, obviously the game has its own goal, but the reward you can interpret it as the our humans' interpretation of the game, or formal. So let's think about this Mario game, right? So Mario game, it has its own goal, and the reward is, if you think about it, it's my own way of interpreting, formally defining Mario game in my own head is the reward, and you may have different reward in your head as well too. And sometimes I might think, surviving is 10, well, surviving could be 50 instead. But getting this right is what the reward designing is about. And the reward has to be predefined, in other words, by human, to train a network. Yeah.
Okay. So based on the reinforcement learnings or the Q learnings, we need lots of try and errors to get the feedbacks from the rewards and then to optimize our goal.
Right, yes. So the question was, do we need a lot of trial and error? I'm not sure which part you mean as trial and error, but I think we need a trial and error for both parts. One, humans have to keep redesigning the reward oftentimes to get the DQN or any reinforcement learning make it work. And you also need a trial and error during the training procedure of the DQN anyway, even given a reward, to get to the reasonable state. That's why you need a million iteration of training sometimes. Which iteration really just means you keep trying some actions based on current Q function, and you update Q plus 1, and then T plus 1, and Qt plus 2, and you keep updating this Q value in the QM framework. And there's a different way of training reinforcement learning, which I will discuss in the second lecture. But in DQM framework, you can think of it as iteration means you keep updating this Q value functions or approximators.
Yeah, I just have one question because
Sure.
We have lots of the examples is from the game,
Games,
but
yes.
for the reinforcement learning. But if the situation is in the manufacturing factory, we cannot lots of the try and errors issue. Yeah,
Yes.
because the physical machines, it will be the cost.
Right.
So did you think about the reinforcement learning? It should be used in the factories, in the manufacturing or not?
Yes. So the question was, many things we are showing is in simulation or games in general, right? Now, so far, all the examples I showed was in games or some toy setups. Can we actually apply to real world? So far, it's only limited, I think. In fact, that's one of you're basically asking me about what is the current state of reinforcement learning right now and what is the next challenge. So the next challenge, as I said earlier in the talk, the lecture, one is this, how to give sparsity word and make it work. And the other is how to make less iterations of training and still make it work. Because if you have to train, there's a couple issues when you actually apply to real world, which is your question. One is that you need, as I said, you need a million iterations. And million iteration of trial and error in real world will take, years, right? If you think about you moving your arm and robots or whatever, if you want to try a million times, no one will do it for you, right? It's just forever. And also the other issue is a safety issue. If you actually have a factory robot moving around whatever way they want, because in the beginning they have no idea about whatever. And you may have a better reward, which is maybe killing human. And then that's basically really going to kill human, right? By mistake, without intention. So there's a safety issue too. So how do we avoid this is, basically we don't know. And is it going to work? Also, we don't know yet right now. But the problem is it just takes too much time with current setup. And one of the ongoing research, actively ongoing research, is how to reduce this training issue. And many things have been done, but so far, one thing one of the most current state of art is first learning in the simulation and applying it, and then applying to real world, not directly, but more with some fine tuning. So you first train in the fake environment where you can try all the random things under safe environment and fast. And then once you get some idea, let's suppose the robot has some idea what to do now, you apply to the real world. Then you still have to adapt to it a little bit, but with a much less number of trainings. And also at least it's less likely going to have crazy actions. But still, this is not nowhere close to, we can call it as a safe or being solved at all. It's basically active, very active research area right now. Yeah. Okay. Oh, yeah. Is that okay to take more question? Okay. Yeah. Well, maybe last question. Sure.
Hello. My question is, how do we deal with multi-agents that we don't have a fixed number?
I see. So multi-agent, yeah, I guess you guys are asking all this active research area. Yes, multi-agent, well, first of all, reinforced learning is very active. Deep reinforced learning is a very active research area. So all the possible, there are many open questions right now, which are some of the things I answered. And your question, which is about multi-agent reinforced learning, is also another very active research area. Although you can think of it in this form, you just have multiple Q function, which depends to each other, which just add a lot more complexity, which makes it harder to train. Yeah, but there's no set answer on how we are doing, what is the right way of doing it right now. Yes. Okay, so I think that's my first part of lecture. We have half an hour break. So yeah, I guess we'll meet in half an hour again then. Thank you.